All right. So if you're in here, you are attending the FOSS at Home track, and this talk is the first one of the day, which is an interesting slot to go in because, I don't know, you get attendees, but then also you set the tone for the day. So let's set the tone. This talk is going to be baking a TuringPi in the home lab. This is not about food, unfortunately, so if you're here about pie, the food, I don't have any recipes for you. I do have chocolate, though, if you're into that. Not here with me, but I do have chocolate. But I'm hoping to give you some inspiration for your home lab. So let me introduce myself first and foremost. My name is Matthew Sanabria. I am currently a solutions software engineer at Oxide Computer Company, and that is my website. Oh, sorry, I don't know if I clicked this little button. Sorry. There's a little switch here for to switch the inputs on the projector. So if I do that again, just let me know. It's in a really bad spot. So anyway, let me go back a slide. Let me introduce myself. I am Matthew Sanabria. I am solutions software engineer at Oxide Computer Company. You can see my personal website on the bottom there, and I think it's probably in the process of deploying now because I just pushed a commit right before this talk. I was going to do more live demos in this talk, but the Wi-Fi has not been great. So yesterday and the day before, I was updating my slides to be more screenshots, unfortunately. But I didn't know I was going to have a hardwire here, so I could have done demos. So here we are. But I have a decade of experience across different roles: systems engineering, site reliability engineering, software engineering. I run Linux where I can, when I can, even if it pains me. Even right now, actually, this is running Linux on this laptop right here for this presentation. I enjoy learning, tinkering, whenever possible, and teaching. So before I begin, what exactly do I mean when we say home lab, right? Because everyone's example of a home lab or definition of a home lab is different. So let's agree on some terminology. What's a home lab? In my words, a home lab is one or more computers that's physically present in your home. Asterisk there, because some people have home labs in various places. But a home lab runs one or more services for your enjoyment. It could be as simple as a spare computer under your desk somewhere or a rack of equipment in your garage or basement. Here are some famous home labs across the internet. If you've spent any time reading about home labs online or watching YouTube videos, you may have actually seen some of these home labs in the wild. You'll see here I have Jeff Geerling's home lab, the Project Mini Rack, on the left. I have Techno Tim's home lab on the right, the Mini Network. I think that video just dropped like a week ago or something. And I convinced my friend to send me a picture of his home lab because he has a much nicer home lab than I do. And he said he'll put it in the Oxide green for me. So that is my friend's rack, no pun intended, of course. So let's talk about some of the goals that I had for when I was building my home lab, right? Because if you're going to embark on some journey building something, you kind of have to set some constraints and expectations up front. That way you don't wander off into nowhere, right? You don't want to just say, oh, I'm going to spend $20,000 or I'm going to spend nothing. You have to have some constraints to keep you on track. So these were my goals and constraints, right? I wanted to understand how things work and have fun doing so, right? So I wanted to, learn, baby, learn, right? That's the song quote. I wanted to learn. I've used Kubernetes a lot in my day jobs, but I've primarily used a lot of managed Kubernetes, and they don't really give you a lot of control underneath the hood. They abstract a lot away from you, and I wanted to get away from that and see, what exactly is happening here. Plus, in my role at Oxide, I am responsible for integrations with the Oxide rack, and one of those integrations, or some of those integrations, are going to be Kubernetes, cluster APIs, cloud controller managers, things of that nature. And the cloud kind of already solved those problems. I want to see how they work under the hood too. Obviously, I want to have fun. If you're not having fun, you should probably take some time to reflect and think about what you're doing and change course. I didn't want to use Helm for my Kubernetes setup, just because I didn't want to deal with the abstraction that it gives me, right? I wanted to understand what I was doing and then make the decision later on to maybe switch to Helm or something different. Also, I wanted to keep it simple and make sure it was publicly accessible because I was going to run things like my website is currently running on my home lab right now. If you go there, that's where it's being served from. So I want it to be simple and publicly accessible. So you're probably wondering, as you should, what hardware I'm using in my home lab. Of course, right? That's why you're here. You want to know what the heck are you running. And note, before I get into it, I bought all this hardware before I worked at Oxide, and now I have access to the Oxide hardware, so maybe I'll move some stuff there. Who knows? But let's cover the hardware. Again, I had some this is the question that was burning in my mind. What hardware should I use? I've kind of been out of the home lab game for a little while now because the cloud has ruined me. So the first question was, what hardware should I even buy? Again, I set some goals and constraints to guide me. I wanted something that had lower power usage because power is not cheap, especially in New Jersey. I wanted a small form factor, setup, ITX builds, whatever, something small. That way I can like put it on a desk or put it in a rack, whatever. I wanted it to be quiet. There's nothing worse than trying to like record a video or like, just read a book or whatever, and your fans are just blaring at you and just, nobody wants that. I wanted it to have multiple nodes because I didn't want to use virtual machines for this. I wanted multiple physical nodes. I wanted a powerful CPU, and I wanted high RAM capacity. So I went with the TuringPi 2.5 cluster board. Now, this board is a 4-node mini ITX board, and it supports various different compute modules that you can slide into those slots. It does have shared network and power, so you just put one power cable into it, one Ethernet cable into it, and you have network across all 4 nodes. And in my opinion, I describe it more as like a home lab blade chassis, so to speak, right? Think of the nodes as little blades that you insert, and that's kind of what I describe it. The deployment process for this TuringPi is pretty simple, actually. You get the cluster board, you get some modules, you plug them in, you connect it to power in the network, you power it on, you flash some operating system, and then you're good, right? Use the operating system however you want. I want to just take a quick look at the TuringPi hardware. So I want to look at the I/O ports on the front of the board, because there's I/O on the front and the back. And there's a bunch of stuff here that I'm not looking at, but I kind of want to highlight a few things. So each of the nodes here is connected to different components. So we have 4 slots that you can put compute modules in. Those compute modules are connected to different I/O ports on the board. So you can kind of run a variety of setups with this board. For example, node 1 has access to the GPIO pins and mini PCI, so you can like put a Raspberry Pi in there or whatever and run some tinkering things. Node 2 is connected to a mini PCI slot for like Bluetooth or whatever. Node 3 is connected to the 2 SATA ports on the board, so you can run storage off of that. And node 4 is connected to USB if you wanted to like have USB peripherals. There's also a CR2032 battery slot for real-time clock usage, right? If you're making use of that stuff. I don't actually have a use for a battery in my setup, but when I see a battery slot, I just got to put a battery in it. So I put a battery in it. There's also a SIM card slot, which I found pretty interesting. If you wanted to deploy this kind of in a remote location or at the edge, you can have that serve as your network connection or a backup network connection. And then typical ATX 24-pin power to like put it in a normal case if you want, right, with a normal power supply. The back of the board is pretty impressive as well. More I/O ports. There's 4 M2 slots. They're 2280 and 2260 lengths. Each NVMe slot or N2 slot is attached to the node on the front of the board, so you can boot directly from the NVMe and not wear out the flash on the board itself. There's also an SD card slot on it where you can put all of your images and flash the nodes directly from there. So that's what I do. I store all my images on the SD card, and then I kick off a flash command to like flash the nodes. That way I don't have to like be at my computer to run the flash. I can just kick it off and it runs. And here are some of the supported compute modules that you can plug in to this TuringPi. You can do the NVIDIA Jetson, right? Various workloads there for like AI, ML. I did not buy those. You can also, if you had a Raspberry Pi Compute Module 4, you could have plugged that in and used your Raspberry Pi. I also did not do that. And then Turing had their RK1 board, which is a pretty powerful chip for its size. It's a nice CPU with up to 32 gigs of flash memory and 32 gigs of RAM if you want it. So that's what I did. I ended up going with the Turing RK1 primarily because I wanted more memory, right? Because the Raspberry Pi CM4 I think only goes up to maybe 8 gigs if I remember correctly. And I think it was like a 4-core CPU if I remember. But the Turing RK1 had more cores and more RAM. So I did that. And here's my build. I got a Fractal Terra case for I think Christmas or whatever, and I was gonna throw like a beefier ITX build in there, and then I was like, wait a minute, I have the cluster board on order. I'll just throw the cluster board in there and keep my other build in my ATX case. My goal originally was to tinker with all of this over the summer of 2024. I ordered the TuringPi stuff in February. It did not arrive until October. So my summer was not spent doing home lab things, it was spent doing other things. But my setup is one TuringPi board, 4 RK compute modules, 4 heat sinks for them, just to keep them cool, just in case. 4 NVMe SSDs, and the Fractal Terror case that I got for free. Total cost came in around $2,200, whatever. Great. Pretty decent compute for the price, I guess, but also you can get better hardware for the same price, of course. We all know this. But I want to turn now to the software. So how does this TuringPi even work, right? I got this hardware in, great. I plugged it in, great. What the heck do I do with it? How does it work? Well, when you plug the TuringPi in and you go to its network interface, or you go to its IP address, you're going to see the UI. You can log in, create your account, whatever. And here's where you can control the TuringPi. You can modify network configuration, you can power cycle the nodes, you can flash firmware, flash the nodes itself, all of this good stuff. And here's just the UI that you can use to power the nodes on and off. It's actually not a great UI, because in order to power the nodes on and off, you have to click edit first, and then click the radio button to move it over. A little weird, but whatever. And then here's the UI for flashing a node. You can just point it to an image, give it a SHA-SUM, and everyone's happy. If you need to find images for the TuringPi, like firmware and OS, you can find some of them on firmware.turingpi.com, but there's not a lot available there, honestly. Like an old Ubuntu image, but whatever. But I'm not a GUI person, and I argue that probably you are not a GUI person either. So I know people here at Scale, they don't use GUIs, they probably use CLIs. And yeah, right, exactly. Luckily, the TuringPi also has a CLI tool. It's called TPI, which I guess TPI, TuringPi, I don't know what it stands for. People don't name CLI tools well, but whatever, it works. You can download TPI from the TuringPi website or GitHub, and then you get access to a variety of subcommands. You can power nodes, you can get the node serial connection, you can flash them, all that stuff. All the things you can do from the web console, but more. So I did that. I was like, oh, okay, let me install TPI. Let me look at the power status for my nodes. Great, I can see the power status. I can modify the power status. I can turn on a node, I can turn off a node. And it was really fast, actually. Like, it's almost as fast as just ripping the node out of the board. You could even flash a node. So I remember I told you previously that I stored all my images on the local SD card on the TuringPi. This is me using an image there to flash the node. So this is what I did. I just kicked off a bunch of flashes and let it go. And then I had Ubuntu installed, and everyone was happy, right? I got, Ubuntu's there. But how do I see the serial console for this stuff? Right? How do I even view what's running or whatever? Because only node 1 has access to the HDMI port on the TuringPi. Other nodes don't have that, so you can't get the GUI. You just need to see the serial. Luckily, the TPI command provides access to get the serial console from a node. You just use the uart subcommand, and you can get the serial console right there in your terminal. However, this is great for viewing the output of a serial console. Not really great for writing to the output, right? If I need to actually log in and type a username here, or a password, or God forbid, switch my kernel, right? If I need to hit something in grub or whatever and switch something, how do I do that? Well, there's also a set command, but it doesn't really work well because you have to get first to view the output, and then see what you want to do, and then quickly type a set command up to do it before it disappears. Not fun. Instead, you can SSH to the TuringPi board yourself and open up a serial connection using PicoCom or whatever, and now you have an interactive serial console. And I use this so much for debugging, for flashing, for whatever, because there were times where I needed to reset my system, and I needed to actually hit the arrow keys to go up or down and select a different kernel or whatever. Speaking of kernel, what am I running on these things, right? Great, I showed you the hardware, I showed you how to use it, but what's actually running on this stuff? Well, I wanted to run Kubernetes, but I had no idea what operating system to run it on, right? There are various different ways to run Kubernetes in the world, but I wanted to see something that was kind of new to me, right? I've used Rancher, I've used these things before, K3s, I wanted to try something new. And again, goals and constraints to guide me. The OS needed to support the TuringPi, minimal bloating, support Kubernetes, be secure, all these things. And I ended up with Talos Linux. And I don't really even remember how I found this, honestly. I think it was a combination of talking to people and some research. But Talos Linux is pretty cool. It's an immutable operating system designed for Kubernetes. Its sole purpose in life is to boot up and be a Kubernetes node. It's weird in the fact that it's managed via the API. There's no SSH, there's no shell, none of that. It's all like gRPC commands, over an API than doing SSH or whatever. It is open source, and it has pretty wide platform support. It can run on the Raspberry Pi, on TuringPi, and all these things. At the time, I was like, okay, I'm gonna use Talos. Now, where do I find an image to put this thing on, right? Like, where do I find a Talos image to run on my TuringPi? Unfortunately, neither the Talos or TuringPi documentation helped me find such an image. There was plenty of images for Raspberry Pis and other things, no images for TuringPi. I ended up joining the TuringPi Discord and researching through there, searching through messages, and I found someone was hacking at this and getting support for Talos. Luckily, I think my timing was just fine because at that time, that hack turned into official support from the Talos side. Like pull requests were created, issues were created, and Talos was like, yep, we're going to support the TuringPi natively on our factory.talos.dev. If you go to that website, you'll see you can download Talos for generic operating systems, for single board controllers, all of these things. So luckily, I was able to download image very easily. So okay, cool, I have Talos. Now let's boot it. So I booted up Talos, and this is what I saw. Just logs. And yes, this is purposefully dirty, right? Like purposefully hard to read. This is what I saw when I booted Talos. Very verbose, hard to read. I even took the timestamps off the logs for you to not burn your eyes. But I know you're still like this. You're still sitting there like, what the heck is this guy showing me, right? And I'm not gonna lie to you. At this point, I walked away from the home lab. I was like, no, we're not doing Talos. I don't want to deal with this right now. When I came back, I cleaned up the logs a little bit, and I was like, okay, what is this really telling me, right? There's a lot of noise here that I don't need. What is it really telling me? Well, it's telling me that I can install Talos in these various ways. So it's booted, but it needs to be bootstrapped, right? It needs to be initialized. And I can do it either interactively or with some config file. Obviously, at this point, I have no idea what a config file, like config.yaml is going to be, so I went for the interactive installer. Ran that interactive installer command, and they presented me with a beautiful TUI, where I can enter the details for my installation and hit next, and then it installed. And great. After it all installed, I just had to download the Kubernetes config file using talosctl, export that, run my kubectl commands, and boom, we got Kubernetes. Everyone's happy. So, okay, one side note here before I go into the custom configuration. Talos is pretty cool in that it can update itself and it can update Kubernetes. So there's subcommands for updating Talos DOS and subcommands for updating Talos Kubernetes. And they were great. They rolled through the Kubernetes upgrades, cordoning and draining a node at a time and going through. Very nice. But I had a question. How do I customize my installation, right? I did the interactive install, kind of went through the defaults. What do I do to customize my installation to do more things? And remember, there was this config.yaml. I had no idea what it was. So I did a pretty novel thing, and I read the documentation. And I found out that you can generate these config files using talosctl genconfig. And all you have to give it is a name of your Kubernetes cluster and the endpoint of where the Kubernetes API is going to be served, and it'll generate 3 files for you. It'll generate a Talos config file, which is just how Talos can communicate to the gRPC API. It'll generate a control plane and a worker YAML, which are self-explanatory, are the configs for running a control plane Kubernetes node and a worker Kubernetes node. Great, I had no idea what to do with these files. I was looking at these files, like, great, what do I do with this again? After some more reading and playing around with it, you have to keep Talos config safe for yourself because you need that to connect to initialized nodes later on. And the control plane and worker plane files are just there for making a new Kubernetes node. I wasn't running worker nodes in my Kubernetes cluster. I was running 4 control plane / worker nodes. And I know that's probably not the best way because etcd, I just increased the quorum of etcd by 1 for no reason. Whatever, I didn't care. It's a home lab. But after much more documentation reading, I found the set of commands I wanted to use to generate my configuration. I generated a new configuration saying, hey, only give me the control plane YAML and the Talos config, forget about the worker, and run a patch. So take the config that's generated and then run a patch on top to do more things. And what was my patch? My patch was just to remove a node label that I needed to remove later, tell it where to install Talos, like what disk to use, and to tell it to, hey, make sure that scheduling is enabled on the control plane nodes, otherwise you can't schedule pods at all. After I had the configuration in hand, here's what I ended up doing to configure my Talos nodes in my TuringPi cluster. I booted them all up, ran the first command to apply the config on all of the nodes. At this point, the nodes were running, but SED was not bootstrapped. So I ran this second command, this bootstrap command, on a single node to bootstrap SED. And then I got my kubectl from Talos, and boom, heck yeah, we got Talos Kubernetes now. Everything's running. Great. Hardware is good, software is good, Kubernetes is up, but I'm running nothing on this right now, right? There's nothing here. So let's talk about load balancing, because one of the goals is to get traffic into my home lab. I need to be able to do that, otherwise I can't go to my website and see anything. So my question was, how does L4 connectivity work to my home lab? L4 being TCP UDP. So you can deploy a service to the cluster right now, right? And this is representative of node port services, right? The green is like one node port service, the red is another node port service. And that's cool. I can port forward those node ports if I wanted to and get access from the internet. But when I do that, I can only use that external port one time for one node port service. I can't share the same port for multiple things. And like, that's fine, we'll get to that later. But at this point, I had no idea, I had another problem. I have 4 nodes. What node do I port forward to, right? Because every node in a node port service can receive traffic and serve it. But like, if I port forward it to like .14, and .14 goes down, everything's broken. And I have to move my port forward to another thing. That seems silly. What I really wanted was some like floating IP or load balancer that I can port forward to consistently, and it moves based on whether a node is alive or not. And I want to just really quickly rant or tangent about load balancers in Kubernetes, because they are very frustrating to deal with. Because every documentation that you read out there is like, hey man, just do this. Type load balancer all day. That's all you need to do, and it'll just work. That's what the docs say. But nobody tells you that something actually has to manage this type load balancer. There has to be a controller running somewhere that like actually makes the load balancer and does the thing. And if you're using managed Kubernetes, all of that's handled for you. You never have to think about this stuff. But when you're using Kubernetes, bare metal or in your home lab, you need to bear this responsibility doing something. And what I chose was probably what you're all familiar with, is Metal LB. So Metal LB, it supports bare metal Kubernetes. It's a layer 4 load balancer, and it uses standard networking protocols like basically ARP, spamming, and BGP. So I installed Metal LB in my cluster, and it can work in 2 ways. You have to give Metal LB like a pool of IP addresses to listen on, right? You say, hey, at Metal LB, this part of my network is reserved for you to listen on. Pick one, manage it, have fun. When you do listen on that address, you can either advertise that you're listening on it using a layer 2 advertisement, which is basically just ARP, right? Or you can do BGP advertisement, which is a routing protocol to like share routes, border gateway protocol. Now, I did this, right? I created my IP address pool in Kubernetes. I was like, hey, Metal LB, you can assign from IP address .50 to .99. And then I created my L2 advertisement and I said, hey, when you do assign an address, spam ARP and make sure everyone knows where you are. And I could create a load balancer type service now using Metal LB, and this annotation just tells Metal LB what specific IP you want to use. If you don't use that annotation, Metal LB would just pick a random one in the range, or probably the first one in the range, I don't remember. And I did that, and nothing worked. Nothing at all worked. The service was there and created in Kubernetes, but Metal LB was not listening on any IP. Honestly, it was not listening on anything. And I was like, what the heck is going on? I had to remove this label from my Kubernetes nodes before Metal LB would work. And I actually don't even really know what this label is meant to do or what controller powers it, is reading this label. But if you have this label on your nodes, load balancer services will not advertise on that node. And all my nodes were control plane nodes, and they had this label. So nothing was advertising. I spent hours debugging this. I'm not even exaggerating, like 3 hours of debugging this thing. I looked at my service, and I was like, hey, I have a service. I tried to curl the endpoint for that service, nothing. Tried to curl the node port itself, not the virtual IP that Metal LB gets, but the actual node IP, and it works. I was like, okay, my service is doing its thing, but Metal LB is not doing its thing. I looked at ARP. I was like, okay, is MetalLB even like spamming ARP? Is it doing the thing? Is it replying? Yes it was. I get a MAC address back. That means it's working. And that MAC address corresponded to the node that it was running on. I even was like, you know what? Maybe I'm doing layer 2 wrong. Maybe my network settings are wrong. I don't want to deal with this. I switched to BGP. Same thing. Errors. After troubleshooting, I realized that I was connecting to the wrong port the entire time. I was supposed to be connecting to the service port, which is on the left-hand side of the port, not the node port. Once I did that, everything was working, and I wanted to just go cry. I was like, oh, well, I'm the problem. And you can see there's a GitHub issue somewhere that I commented on saying, like, what's going on? It was me. So let's move off of load balancers into ingress. Now, I had traffic coming into my machine, or into my cluster. Great. How about L7 connectivity, right? Can I share the same port and serve multiple services with that port? So as a reminder, this was my architecture up to this point. I had MetaLB, kind of giving us that floating IP model, and I was able to port forward in from that, no problem. But I really wanted a model like this. I wanted to have some layer, probably Nginx, running, listening on port 80 and 443, and then it could divvy out, oh, you came in on foo, you came in on foo, you go here. You came in on bar, you go there. That's what I wanted. And I needed an ingress controller to do that. I use Nginx ingress controller, as most of us probably do for Kubernetes. It's very popular, and that's probably the only reason why I use it, because everybody else uses it. I created my Nginx ingress, I deployed the operator to the cluster, and then I created my Nginx ingress. I said, hey, please run as a daemon set, and please listen on .50, because that's where I'm going to port forward my port 80, port 443. I will always forward it there. I didn't need to use a daemon set, but I did. Then I was like, okay, let me create a test, make sure this works. I created a deployment in a service that was listening, right? And I created an ingress to say, hey, anything that comes in on matthewsanabria.dev, send it to the website service on port 8080. Great. I had DNS updated, everything was working. The resources in Kubernetes looked good. I was able to get the ingress resource, get the controller resource, everything was happy, and yeah, my test case was working. Great. But what about TLS? Right? I'm serving on clear text, but I'm serving on HTTP clear text, but I'm not serving on HTTPS, encrypted. So that was my question, right? HTTP is great. What about HTTPS? And then this is where I said, okay, Cert Manager looks good. Did some research. It supports TLS certificates, popular protocols like Acme via Let's Encrypt, and it does renewal all itself. So I deployed it to my cluster, and I created a cluster issuer so that any namespace on my cluster can request a certificate. I told it I want you to use the Acme protocol to get certificates via Let's Encrypt, and I wanted to use the HTTP challenge in order to actually get the certificate. In hindsight, the HTTP challenge was probably a mistake, but I did. I went back to my ingress for Nginx, and I was like, hey, added this TLS section on the bottom here. Please request a cert from Cert Manager to get TLS working. That was all good. Looked at my ingress here, and I was like, wait a minute. What's going on? Nothing's working, right? I see the certificate trying to create. I see everything's looking good, but the challenge is not being fulfilled, right? Because Let's Encrypt via the HTTP challenge will send basically an HTTP request saying, hey, does this file exist on your endpoint? If it does, I verified you. Here's a cert. Nothing was working for me. Again, after hours of troubleshooting, I realized that I had to add this annotation, to my Nginx ingress because Nginx was taking all HTTP connections and redirecting them to HTTPS. So that challenge that was coming in on port 80 was immediately being redirected to 443. Nginx was like, hey, here's the invalid certificate for that. And Let's Encrypt was like, failed. It took me forever to find this annotation because there was 2 pieces of documentation that had different annotation names. Very, very frustrating. Once I added that annotation, everything worked, and I had a certificate. I was able to see my cluster issuer, my certificate request, my certificate was there, valid, everyone was happy. And now I go to the test page, and we're served over HTTPS. Okay, everything's set up now, right? I have all of the plumbing is there. Let's put a real app on this thing. So the first thing that I wanted to migrate was my website, right? My matthewsanabria.dev blog. Pretty low risk, whatever. So I was like, let's test this thing. So my website is listening at matthewsanabria.dev. It's running on the home lab now. It's built with Hugo, which is a static site generator, and all that means is it takes a bunch of Markdown and makes HTML out of it. It was previously hosted on DigitalOcean, and I had a very bad experience with their app platform. I hated their app platform, honestly, so I wanted to get off of there. So I moved it to my home lab. How did I do this? Previously, I had a Docker file. I'm not meant for you to read this, really. This is the Docker file I used to deploy to DigitalOcean. One thing you'll note, though, is that all it does is build the site. It doesn't serve the site, because DigitalOcean is very weird, and it wanted you to like build the files, and then it would copy it out of the container and serve it itself. And I'm like, this makes no sense, DigitalOcean. Just run my container. So I moved it, and I used a multi-stage build to build my Hugo app, and then serve it via Nginx. Nothing too crazy there. So I created a deployment to deploy my website, right? Simple deployment running this container. I exposed that deployment as a service. This time, you'll notice that the service is not of type load balancer. It's just a cluster IP, because Nginx is my ingress, and it's going to be able to handle that. And I ran it. And that didn't work, right? So I was like, okay, what's going on here? I got this beautiful error. And does anyone know, does anyone have an idea of what's happening here? Yes, kind of. Any other guesses besides ELF? Mismatch of architecture, exactly. I was building these container images on my framework laptop, which is AMD 64, and I was pushing it up to GitHub to serve it, and it was running on my TuringPi, which is ARM 64. So we're not in AMD 64 land anymore. So at that point, I was like, for real? I was like, really? I used Podman's BuildX feature to do an emulated build for ARM, whatever. And I was like, I don't want to do this anymore. Made a GitHub action. This is like a typical setup for GitHub actions. Log in, set up the emulator, run your build and push. So I did that, and now I have AMD and ARM builds pushing to my GitHub registry. Great. At this point, though, I don't have a deployment process for my website. I just kind of run the container myself, or run the deployment myself. If I created a new image and it got pushed up to GitHub, there's nothing that would redeploy it for me. This was my redeployment process, me just running rollout restart. Of course, that doesn't scale, but we'll get into that later. And here's now a reminder of how traffic was flowing in. Same diagram from before. I'm listening externally on port 80 and 443, forwarding that to Nginx's ingress controller, and then from there, the ingresses are going to various services. Great. Another problem. What about dynamic DNS? What happens when my public IP of my house changes? Because they can do that, right? My ISP can change my IP, or if my modem's down for an extended period of time, I'll just get a new IP via DHCP or whatever. What do I do? So I am running unified networking equipment or Ubiquity networking equipment at home. It supports a dynamic DNS feature where anytime the WAN IP changes, it'll send a request to say, hey, do something. And I needed to speak this dynamic DNS protocol. What exactly is that protocol? Well, it's just a request, a GET request to /nic update, and it gives you the IP and the host name to use using query parameters, and the response is always going to be HTTP 200 OK with error messages inside. So very annoying that it uses HTTP 200 to mean OK and error, but whatever. My next question was okay, if I implement this protocol, can I run this as an internal service? And I kind of went a little wild here in my mind. I was how do I run an internal service? Do I do another ingress? Do I do this? And I was no, silly. I can just make another Kubernetes service and run it on a different IP. It's fine. So that's what I did. I wrote a program, spun it up as a container, put a service in front of it, and the unified controller wants TLS on that, and I didn't have a way to do internal TLS certificates easily. I mean, I could have done self-signed via Cert Manager, but instead, I did self-signed and I stored it right in the program itself. So if you go to the GitHub that's hosting the service, you will see a TLS cert and key. And I don't care because it's self-signed and it doesn't need to be validated for anything. So you're probably asking okay, Matt, what does this program that you wrote look like? Well, it's available on my GitHub, sudo Mateo, unified dynamic DNS. You can see it. It's not the best code at all. I wrote it on the airplane here. And all it does is it receives a dynamic DNS request. It will take that request, say, hey, I have a new home IP. I will update a variable that I have in Terraform Cloud for one of my workspaces, trigger a run, and then all my DNS records get updated to the new IP. Very nice. And that's basically the basic flow. It's not foolproof, right? Because there's a chance where the update can come in and my program is either not running or whatever, but it's good enough. And I want to move into now CI/CD, because up until this point, I was deploying everything manually. kubectl apply this, kubectl delete that. Everything was being done at my keyboard. So I wanted to know, hey, how do I deploy this stuff automatically? So I wanted to set up something to do that, but I didn't want it to be like Helm, right? So enter flux cd. Sorry, this is like slipping off my bald head. So I ended up choosing flux cd for no other reason than it was either Flux or Argo, and I've never used both of them, and I rolled the dice, right? Here you go. I bootstrapped Flux into my cluster, which installs all of the necessary stuff into the Kubernetes cluster. And Flux is basically, the way it works is, you have controllers running in your cluster, it's looking at a GitHub repository, in the GitHub case, waiting for manifests to be pushed to that location, and then it'll pull those manifests and apply them to your cluster. That's basically the flow of Flux. So I configured a Git repository. I said, hey, look at this location, this home lab location. All public, by the way. You can go browse. It's fine with me. Every 1 minute, check. See if there's any new manifests. If there is, pull them, apply them. Flux also uses customization, to my knowledge, or at least to my reading. Now, I didn't do anything special with customization at all, but I think Flux needs it to operate, and I didn't do anything more than just let it do its thing. I'm not doing any customization thing. Maybe I will in the future. But if I wanted to trigger a Flux like reconcile, I can do that via the CLI. I can say, hey, Flux, reconcile yourself and check for updates. And that's great. But I did have a problem, though. What about updates to my container images? Because at this point, I was using like the latest tag, and I was just restarting my deployments. That's not a good practice, obviously. So I wanted to have the images update automatically using like a better tag that's not latest. Here's a reminder of what I was doing up until this point. I was just doing a rollout restart. Now, it turns out Flux actually supports image updates. I didn't know this at first until I read more of the documentation. But you can tell Flux to watch a registry, like a container registry, for changes, right, for new tags. So I did that. I created this image repository resource using Flux. I said, hey, watch my website repo for new tags every 5 minutes. And then I wrote an image policy, because in order for you to, this is great, that allows Flux to get new tags, but there's no ordering to these tags. How do I know if this tag is newer than this tag, right? It's all git shaws at the end of the day. What is new? So I used a pattern, like I made tags of a certain pattern with the branch name, the short commit, and then timestamp. And then I told Flux to pull out the timestamp, because that would be a monotonically increasing integer, right, epoch time, and use that as the ordering. That's new. I then updated my CI/CD process to build containers with that tag, right? Get the SHA, get the time, put it on the tag, have fun. And then after that, I know this is probably hard to read, but I had to tell Flux, once you've pulled new tags and you've ordered them in a certain way, what do? Right? I told Flux to go to my repo. When you find the new tag, go to my repo, go to this website.yaml file, and push the new tag as a commit to that repo. Because then, that'll push the new manifest to that location. Flux would then read that new manifest and apply the stuff. So I had all of this nice automated deployment going. But you might be wondering, how the heck does Flux know what line to update? You have to give it this little tag here, and that's basically just like a field tag that tells Flux this is the line you should update with this image policy. So anytime Flux sees a new tag, it'll find this line and update it. And now I had automated updates. This was not me, this was the Flux bot doing this, and I had automated updates working. Everyone was happy. And I did push a new commit before I started this talk, and hopefully it's live on my website. It just says hello scale, essentially, on my website. So yeah, that was GitOps, right? I don't even like the term GitOps, but I was doing GitOps. Great. Let's move on. There's more stuff. There's always more to do. I had, up to this point, no persistent storage, right? My website was built as like basically a static binary, essentially, and deployed. But I had no like persistent storage, no databases, no nothing. So what can I do about persistent volumes? Well, enter Longhorn. Now, I'm not really too familiar with the different CSIs that are out there, container storage interfaces, but research led me to Longhorn, It seemed to be a pretty good distributed block store that can work on your bare metal clusters, and it was part of the CNCF. This is a general architecture of Longhorn. Basically, those SSDs that are on my TuringPi, Longhorn would look at those. It'll like make replicas, expose that replica to you in your pod as a volume, and just manage all the storage for you. Very nice. I applied Longhorn. Great. Everything was great. I then tried to create a volume, but Longhorn wasn't even running yet. Even though I did the apply and those services were created in Kubernetes, I was getting like crash loop backoffs or whatever. And I was like, what the heck's going on here? I had to update my Talos nodes to mount varlib Longhorn into the kubelet. I didn't really know why I needed this, and even people in the TuringPi Discord didn't really know, but I did need this to work before Longhorn would start up. It looks like I did some extra research of my own. It looks like the way Talos works is it mounts /var as like an ephemeral volume, and ephemeral is a really bad term here because it's a persistent volume. It survives reboots and stuff, and it's actually where Talos stores the etcd data for the cluster. So I mounted Longhorn into there, everything was working, Longhorn was up. And now I was like able to create a persistent volume claim, and I had volumes. Everyone was happy. I mean, everyone being me, I was happy. Great, I have volumes. Let's deploy something that uses the volume. So I wanted to deploy a test application to my cluster that makes use of this new persistent storage that I had. And what did I choose? Pi-hole, right? It's such a simple app to deploy, super low risk, but it also needs persistent storage because it stores its records and such and configuration in a database. Plus, I haven't really made use of Pi-hole much before, so I wanted to give it another go, right? I deployed Pi-hole, I created a new namespace for Pi-hole, I got my persistent volume claim, I said, here, Pi-hole, that's where you're gonna store your volume. I created my deployment. The deployment is just running the Pi-hole image and mounting the volume into like a directory on the container. And I had to add this DNS config before Pi-hole would like work with DNS. I didn't know why, so I left myself a to-do to figure that out later. Then I exposed Pi-hole as a service. I was like, okay, Pi-hole needs to listen on port 53, TCP and UDP, because that's what DNS does. So I told Pi-hole to run as a load balancer service on 99 and expose 53 TCP and UDP. Now, like, when I was doing some reading here, I read that a lot of people use two services for this. They separate a TCP service and a UDP service. I didn't see any good reason for doing that, so I left it all as one. So if you know a reason, let me know after the talk. Everything was deployed. I tested it. DNS was working. Great. You can see the initial request was, a cache miss, so I had to like actually go out and do an authoritative lookup, and the rest of them were served from cache, so they were much quicker. And then I had one more app that I wanted to deploy to this home lab cluster, before I kind of ran out of time. What about something else? What about a stateless app? Let's deploy a Discord /command to the home lab. I have built very trivial /commands before, and I wanted to like use this as an excuse to over-engineer a bit and tinker. So I deployed an app that I wrote called yeetcode. It's just a /LeetCode command that retrieves a random LeetCode question from LeetCode. I have a Discord server where I help people like in their career development, and we do a bunch of LeetCode together. And we would always like select the first question and do it, and then we're like, what's the next? I don't know, what's next? And then we're like, you know what? We'll just make this a computer's problem. Let's pick a random question. And that's what this program was. So I ran it on my home lab. I created a new ingress. So it lives at yeetcode.matthewsanabria.dev. It's a new ingress, new TLS cert, whole 9 yards. And this is how it works. You just run /LeetCode, and it prompts you for the difficulty. And you give it easy, medium, hard, because that's the only 3 difficulties for LeetCode. And it'll send you a URL for the LeetCode question. Now, if you've never built Discord /commands before, it's really like 2 parts. One part is you have to tell Discord the definition for your /command. You have to say what the command is, the options that it supports, all of that stuff. And then you have to, sorry, I was just looking at the slide again, making sure it wasn't cut off. And then you have to deploy your service that handles the /command. So what happens is when someone types the /command in Discord and hits enter, Discord will read that, send your app an interaction, it's called. Your app has to verify the interaction and respond to it. That's the whole setup. So I did all that, it worked, and here's it running, me spamming the command a few times. But let's have some fun, right? What about telemetry? Like, how do I see this application and what it's doing? I used OpenTelemetry in this app to send application tracing to Axiom, and I figured I'd wear the shirt because I need to save my Oxide shirts for next week. So I instrumented my app with tracing, right? I got rid of all the logging, all the metrics, and I just did tracing, and I sent it all to Axiom. This code here is just Go code that says if the Axiom API key is provided, send traces to Axiom. If the Axiom API key is not provided, send it to standard out, right? It's pretty simple. I didn't end up using the OpenTelemetry collector here just because time. I didn't really have time to set it all up properly, and I've used it very extensively in my career, so there was no new learning there for me. So I was like, let me just skip that and just send it from the app directly. Axiom has a little weird quirk that traces have to have a parent span ID in order for them to be visible in the UI. If they don't, they're just not visible. And I had everything as one big span instead of doing child spans. So I was like, okay, let me just move a function out and make a child span. And that's what I did. And then once I did that, I got this beautiful dashboard in Axiom that showed me the number of spans I'm getting, how many spans per minute, the duration of those spans, just general. This is a canned dashboard that Axiom provides once it sees that you're sending data. Cool. But I wanted more information, right? If I clicked on a trace, I can see that, okay, when I receive the interaction, I take 652 milliseconds to respond to it. Of that, 489 milliseconds is spent fetching a question from LeetCode. I can definitely optimize that by pre-fetching a couple questions and storing them in cache, but it's a home lab. Who cares? Right? If this was a system design interview, that would be my answer. Here's my offer, have fun. I then wanted to create a more custom dashboard. And I want to say hey, I wanted to answer two questions. What's the breakdown of the easy, mediums, and hards that are being requested? And what are the latest questions that were being requested? So I created this dashboard in Axiom. Very simple. And here's the code for those dashboards. Axiom has a piped language. It's called APL, Axiom Processing Language, I think. And it's basically it's kind of like a Splunk-like language if you think about it. And you can just query your data like that. So these are the queries that power that dashboard. Cool. And let's start to wrap up a little bit with some of my lessons that I learned from doing all of this stuff. I know I've been kind of talking at you for 40-something minutes now, but let me tell you some of the lessons I learned. Lesson number one, the cloud has ruined me. Not gonna lie. All the documentation for Kubernetes and home lab things or whatever always assumes that you're running in the cloud. The cloud abstracts all these things away from you and doesn't tell you the magic that's happening under the hood. And honestly, when I looked at it from a more objective standpoint, using the cloud throughout my career, I'm not saying the cloud sucks. That's not what I'm saying. But using it so much and relying on it so much really atrophied my skills as an engineer to learn things on my own. Right? I just kind of relied on the cloud to solve it for me in the name of solving business problems, but then I was less marketable because I didn't know what was happening. So this home lab work and the work that I'm doing at Oxide helps me remember why I love this field in the first place. I love knowing how computers work, actually work, not just making, hitting a button and it works. I want to know how things work. Another lesson was I needed to leave some time for debugging. As I told you, I spent hours debugging very simple problems, and it's just because I didn't know what I didn't know. So if you're doing new things in your career, leave some time for failure so that you can recover from it. Also, another lesson I learned was annotations are wonderful and scary. A simple annotation can do wonderful things for your Kubernetes cluster, but it can also break everything. So just be careful and read the documentation for the annotations. But also know, documentation for whatever you're doing might not exist, and you are the best source of documentation through your trial and error. Also, remember to ask questions. It doesn't show that you're not smart, it just shows that you're curious. And what am I going to do with this home lab in the future? I'll run through this really quickly. I'm going to break things up into multiple namespaces. Everything's kind of deployed in the default namespace right now, and I want to break that up a little bit. But deploying an Nginx ingress controller across multiple namespaces is a little complex, and I don't really have time for that. I also want to use secrets integrations, so that way my secrets aren't just manually created by me, they're stored somewhere else. Maybe the 1Password operator, I don't know. I want to deploy and document more. I have more services I need to run on the home lab, but I just didn't get time to do it. And I want to write some more controllers, right? Actually, I want to write more operators, but I really don't like the term operator for Kubernetes. It's a really, really bad term in my opinion, but I do want to write more operators for my home lab. And then 2 more things. I want better observability. I'm getting no metrics from the Kubernetes nodes right now, not because I don't want to, I just didn't have time, right? I'm not using kube state metrics yet. I'm not getting node health, CPU, memory usage, none of that. I also don't care so much because there's not much running on it yet, but whatever. And then lastly, I want to have some concept of disaster recovery. I'm not backing up any of my volumes. I have no written plan if anything goes wrong. If you were to go to my home lab and steal my TuringPi, okay, I have nothing like ready to recover from it. I will get there. And with that, I just want to say, go out there and home lab. I hope this talk has inspired you to just tinker and learn. And yeah, thank you for having me here. Okay, I had no idea that this was going to be an hour talk, but I'm glad that I got to fill it. And I'll be here to answer any questions for y'all.
Did you create do you have a HA setup for your API service?
Sorry?
For the API gateway, do you have a HA setup for that?
No, no. It's just the Nginx like ingress controller running as a daemon set. So technically MetaLB should fail it over to a different node, and then that node can handle it. But it's like, is that really HA? It's all running on the same board, so.
Yeah, because Talos is still big setup if you want.
Oh, you mean for the Kubernetes API? Sorry, I misunderstood you. Yeah. Yes, I am. I'm using the virtual IP feature for that. But like.
One issue I ran into with that was it depends on SCD.
Yeah.
The SCD stuff.
Yep.
So I just ended up.
And I ran into that when I was doing the rolling upgrade of Kubernetes. The node that had the virtual IP for the Kubernetes API, when it goes down, you're just like, okay, I'll just wait 10 minutes. See you later. Yeah. But it works okay though for what it is. At least they tell you that in the documentation. You know, so that was good. Any other questions, comments?
Yeah, you're lucky you didn't have the switches we had 20 years ago.
Oh, I believe it.
The hardware switches, you had to put some fuck it. You got everything, software, identifies, conflicts,
Yeah.
ports.
Oh, I get it. I remember deploying some old equipment, and I love what I have today. There's a lot of good hardware out today.
How did you get the first image on your Turing platform?
Before they had it on factory, I just scoured the Discord. I asked questions. I was like, hey, I see you all are building images. What are you doing? And then people really didn't give me much of an answer except for here's my GitHub repo. And I just kind of like read it, hacked at it, and pulled. Some people had built images already without Talos extensions, and you need some extensions to run things like Longhorn. So I used those at first, and by the time I got to the need for Longhorn, the images were already up on Talos. So I switched to that. But the initial image, I either built it myself or downloaded it from some random person's GitHub.
Follow on, in the standard standalone Pi world, you image the SD card, stick it in and go, but you've got 4 on that board. How do you get into it?
Oh, yeah. Okay. So each node has flash memory on it that you can run the OS off of if you want. But some people say don't run the OS there because it just hits the lifespan of the flash. I'm running the OS on the NVMe that's attached to each node, and I just flashed each node one at a time. So what I did was I flashed each node. The OS was running on the flash of the node. Then I went into the node, copied the OS to the NVMe, and then rebooted, and it booted from the NVMe.
And then all subsequent updates go to the end.
Correct, yeah. This is also documented on Talos' website now. If you go to like Talos and search for TuringPi, you'll see a way to run TuringPi off the NVMe instead of the flash. So I just followed that process. Yeah.
If you're running a system, because this looks like it's mostly CPU and RAM.
Yeah.
What about solid state drives and things of that nature in that system?
Yeah. So the question was like, what about other hardware? Like, the TuringPi is mostly CPU and RAM. What about SSD? On the back of the board, there's NVMe drives that you could attach, and they link to the node.
Some kind of limitations is the size.
No, I didn't see any limitation on size. I put 2 terabyte drives in there. I'm never going to reach 2 terabytes of usage on that thing. But I guess you can probably go up to like 8 or 16 or whatever M2 drives are nowadays. I don't know what the max is. But anything else? Questions?
So RK1 requires a specific build?
Correct.
Okay.
Yeah.
So I don't have my, long story, it's in the queue to get my board, but I've got like 4 RK1s.
Yeah.
And I was just like, oh, I just throw a Raspberry in there.
That was my thought at first too. I was like, oh, this is it's like a Raspberry Pi, right? No, it needs a specialized driver or a specialized OS for it, like an OS image. And
How many are
From what I've seen, Ubuntu is one of the more supported ones, although I looked at the TuringPi Discord and the person that was maintaining the Ubuntu stuff was like, nah, I'm done, man. So I don't know what the future of that is. Now that Talos has it as their official image, I think that's going to stay supported. Everything else is like, you probably have to go hunt around the internet, which is one of the drawbacks for getting the RK1. It's a powerful board. Like, that thing slams. But good luck trying to find an image. You're pretty much on your own for that, which kind of sucks. But it's getting more popular, though, because more devices, not just the TuringPi, are using that chip and starting to become more popular, which is good for us home labbers.
Can you mix the boards?
Yes. Oh, yeah. You can mix and match modules on the TuringPi if you want, because like different modules are connected to different peripherals, and you can mix and match them. I could have done that, but I didn't.
So you said like slot 3 is SATA, right?
Yeah.
So you're saying that's the only board that has access to SATA?
Correct.
And then like, what was it, 4 has USB?
Correct. 4 has the USB headers. Node 1 has HDMI. Node 2 has pretty much nothing except for mini PCI. But yeah, so you can like put your GPU module in one slot. You can put like a generic module in slot 3 and provide storage. You can just mix and match. Which, I mean, I get it. There's only so much bandwidth because the slots are just DDR4 slots. That's all they are, right? Because I don't know if everyone knows, but DDR4 is not just a memory. It's not a memory type. It's actually a slot specification. You can put memory in that slot, but you can also put other things. So this is just a DDR4 slot, and there's only so much bandwidth that slot can handle. So I guess they mixed up the peripherals to account for that. But yeah. But they do all share the network. They do all share the power.
So for a storage strategy, like what we do with Longhorn, that's the way to get some resiliency in the storage side. But otherwise,
Yeah, that's the Longhorn is probably the most expensive way to get the most storage. But you could, the documentation on TuringPi for Kubernetes, an alternative way is to have Node 3 be an NFS server and have the SATA ports that are attached to it, you know, plug a 2.5-inch drive in there and serve that and use that for your Kubernetes storage. Then you have a single point of failure, which is why I didn't do it, yeah. I wanted to be able to pull out a node and not care, if I wanted to. Granted, yeah, I'm still sharing power, still sharing network. I don't care about that. I'm not a data center at home. I just wanted to be able to like mess around. Right. Exactly.
Yeah, most data centers have 2 power sources, one
Right.
laptop, the other one.
Yeah, I was just in a data center like last week doing an Oxide installation. And it's amazing how cool they have gotten over the years. But any last minute questions? I can put them up. I'll probably just put them up on probably my, you know, that GitHub profile link, or I'll probably just put them up on my website or something, somewhere there. I'm not gonna lie, I finished them last night, so I didn't get a chance to put them anywhere. Cool. Well, thank you everyone. Really appreciate you coming here.